I just got home. I had an organic chemistry exam today, and I'm just going to show you guys what I learned from this exam, just based on the questions that people have tended to ask me. So if you guys don't know, this is my second channel. I do have a personal channel that's just called my name, Richelli Storen, and that's more like vlog style videos and like MCAT style videos as well. But I decided to make this second channel to make more actual content related videos and educational videos, so like explaining topics like biochem, organic chemistry, and just doing some MCAT walkthroughs as well. Just learning some mnemonics and making the intro or your first orgo exam just a little bit easier, because I know at first it can be daunting. And I mean, I just don't want to get shit on by this class. So I just wanted to show you how to name straight chain alkanes, just getting used to the concept of orgo and organic chemistry in general. So the only knowledge that you need to have in order to kind of understand this specific video is Lewis structures and just electrons, valence electrons, and just how many bonds things can form, especially carbon. But essentially, this is what a straight chain alkane can look like. Obviously less wonky looking, but this is the idea. And you're gonna have questions that look like this, and they're gonna ask you to name it. Probably not that simple. They could look like this and ask you to name it. They could look something like this and ask you to name that. So at first, like I said, this is going to be daunting and you're going to be confused, and that's completely normal. I'm going to clarify what all of this means. So I'm going to start off with just a super long straight chain alkane, and this is an alkane because it's carbohydrate bonds without a double bond. So they're just single bonds without a double bond or a triple bond. Okay, so that's an alkane. They're gonna have the ane ending, which you'll see what that means in a second. So I'm just gonna give you guys an example of how you can actually read one of these drawings, right? So I'm gonna draw something like this. So if you are not familiar with how to read this at all, I'm just gonna give you a quick rundown. The easiest way to do it, at the end of every line, there is a carbon. So by labeling them or putting a little circle or dot on it, you're able to count your carbons. This is carbon 1, 2, 3, and 4. So this has 4 carbons. Okay, let me give you a different example. What if you had something like, oh my gosh. What if you had something like this? If you want to try it on your own first, I'll give you a second. Okay, so for this one, you would have 1, 2, 3, 4, 5, 6, 7 carbons. So that's basically the idea. And if you were to have something like 2 carbons, it would just look like a straight line, because each end would count as 1 carbon. All right, so this is what we have for these straight chain alkanes. Now you know how to count the carbons on any one of these drawings. These are the more simple drawings, and I know they get more complex. Trust me, I just want to start off simply and then get more complex as the video goes on. So if this is something that is very obvious to you, just skip forward. I am going to put timestamps in the description box so that you don't waste your time like relearning things that you 100% feel comfortable with. So the next thing that I want to show is how you can actually name these compounds or these structures. So the parent chain is the longest continuous carbohydrate chain, right? So this would be the longest continuous carbohydrate chain. There's no breaks in it. It's just carbon, 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 right? Now, the thing that's important here is that what this really looks like is this. I'm just going to redraw the same thing, but showing the carbons. And remember, carbon can form 4 bonds, and in these alkanes, it's kind of assumed that all of these, unless shown otherwise, are bonded to a certain amount of hydrogens to fulfill those 4 bonds, right? So this carbon has 1 bond. Let me show. So this carbon has 1 bond to this carbon, right? I'm talking about this carbon right here, by the way. So this first carbon only has 1 bond right now, which means to fulfill the 4 bonds that it needs, I'm gonna add 3 hydrogens. And this is all assumed here. That's why here in these linear structures, you don't see the actual hydrogens. as you would on like a skeletal structure such as this one, because they're assumed. We know they're there, but they just don't draw them. So these linear structures are just for simplicity. You know, it's easier to draw this than to write this whole thing out. So now for the next carbon, this carbon right here has 2 bonds, 1 to each carbon. So that means we're going to add 2 hydrogens to fulfill those 4 bonds that carbon loves so much. Next one, same thing. This carbon has 2 bonds, so we're going to add 2 hydrogens. So I just redrew this top structure into a skeletal structure. Now, when you get to actually naming these, I have the first 5 carbon groups as a mnemonic. It's kind of a dumb mnemonic, but it works. It's just Mary eats peanut butter peacefully. So I'm gonna write that down. So this each stands for an added carbon onto the chain. Mary is for meth, for methane. This is for ethane, propane, butane, and then 5 is gonna be pentane. And then the rest I kind of feel are a little bit obvious. So 6, we have hexane, 7, we have heptane, and so on and so forth. So this is basically how you're gonna name these compounds. So I'm gonna use this 4 carbon example again. I'm just gonna draw it again over here. It's the same image. I could also draw it like this, same thing, same amount of carbons. 1, 2, 3, 4, 1, 2, 3, 4. It's just a different orientation. It's just a way of shortening it, okay? So these are the same compound. Don't worry about that. Now, what we're gonna look at is how we're going to actually name this. So what is this called? Okay, so we have 4 carbons and it's just an alkane. There's no functional groups, there's no substituents or extra chains on the side or anything complex yet. So there's 4 carbons, nothing else added. So we're gonna call it butane. So this is butane. And this is also butane because they are the same structure. 7 carbon, straight chain alkane with nothing else on it is just gonna be called heptane. Now let's get away from this clusterfuck of information that's going on this page right now. And let me just give you guys 2 more examples before we move on. So I'm just gonna put, I don't know, I'm gonna put something like this and then give you something like this, just to make it a little bit more complex and move forward. Because realistically, the odds that you're just gonna get straight chain alkanes with no functional groups are pretty low, but it does happen. But I need to teach you how to add substituents and how to make it more complex. So first things first, how many carbons does this alkane have? 1, 2, 3 carbons. What are we gonna call that? Mary eats peanut butter. What's the 3P for? Propane. This is propane. At first it's a little uncomfortable, like I said, but eventually it's gonna come to you super quickly. So don't feel bad if this part is a little stressful. Or maybe it's super easy and you're like, bitch, shut the fuck up. That's fair enough. Now, when you have a closed structure like this, count the carbons. Each corner is a carbon, like the straight one. 1, 2, 3. But the difference now, because it's a closed structure, it's a cyclic structure. This is going to be called cyclopropane. Same thing. When we had this, which was butane, 1, 2, 3, 4, if we were to draw it like this is cyclobutane. We're going to use this naming structure every single time because it's always going to apply. Whether there's a functional group, you're always going to have a methyl, ethyl, propyl, whatever. So let's keep it going, make it a little bit more complex. Now, let's do something like this, right? First thing you want to do to name this, we're going to find the longest continuous parent chain. So what the hell is a parent chain? It's just the longest continuous chain like we were doing up here. The parent chain is heptane. The parent chain is ethane. Whatever the longest continuous chain is, let's find that. So I'm going to use the same color as before. 1, 2, 3, 4, 5. Is that the longest chain? I'm going to use a different color to compare to see if there was another way we could have counted it. 1, 2, 3, 4, 5. Kind of the same thing. So I'm just gonna stick with my pink one. So we're gonna say that the parent chain is 5 carbons. What's 5 carbons? Let's reference our little table. 5 carbons is pentane. So I'm just gonna write pentane. So now we know that the parent chain is a pentane because the longest continuous chain is 5 carbons. 1, 2, 3, 4, and 5, right? Now, the second one is we want to figure out what the substituent is. What the hell is a substituent? A substituent is whatever is hanging off of that long parent chain. So we see that this group didn't fall into the longest chain category. So we're going to call that something. How many carbons are on that little hanging group? Just 1 that are not part of the main chain, right? So what is that going to be called? That is going to be called a methyl group. Why is it called a methyl and not a methane? Because you add the YL ending whenever it's a substituent or like a little branched off chain. So if it's a branch, you're going to add a YL ending. So this is a methyl group. So now we're going to try to, we know it's a methyl is a substituent, just 1 methyl. That's not a part of the long chain. Now we want to put a number on that methyl. We want that methyl or whatever the substituent is to have the lowest number. And what I mean by that is we're going to try to count these carbons so that methyl is on the lowest numbered carbon. So there's 2 options here. We can do 1, 2, 3, 4, 5, or we can do 1, 2, 3, 4, and 5. So in the purple option, we have methyl is on number 2, or we have methyl on number 4, right? And obviously we want to prioritize the one that has the lowest number because we're giving it importance. It's like you want it to be first in line. You want methyl to come first because it's hanging off the side and it's special. So we want the substituent to be on the lowest number, which is going to be 2. So now we're going to order it in alphabetical order with the parent chain coming last. In this case, the alphabetical order doesn't really matter as much as later because we only have 1 substituent, so it's the first one that comes. So we're going to do 2-methyl and then the long parent chain, which is pentane. So this is telling you the substituent and this is telling you the long parent chain. And this is telling you the location of that substituent, okay? Now let's do another example. Let's do one like this. Okay, this one's a little bit weird. Now we're gonna do the same thing. We're gonna find the longest parent chain. We're gonna pick what the substituents or side branches are. Let's see what the longest chain is. 1, 2, 3, 4. Is that the longest chain? No. 1, 2, 3, 4, 5, 6, 7. Is that the longest chain? Seems like it. Can I do 1, 2, 3, 4, 5, 6, 7? Yes, but it's the same thing. The branches are on the same carbon either way. So this is what we're working with. We have 1, 2, 3, 4, 5, 6, 7. So parent is going to be the 7 carbon name, which is a heptane. Right? This is the parent. This is going to be at the end. Now we're going to find the substituents, which are what substituents? So what do we have here? We have 2 substituents that are not a part of the main carbon chain, and that is this one and this one. I'm using the ugliest colors in the fucking world, but that's okay. So I have this one and this one, which are the 2 substituents that are not part of the carbons that I counted. And what are these groups called? These are both going to be methyl groups, right? But they're on different locations. Last time we only had 1 methyl group. Now we have 2. So what does that tell us? We need to do the same thing, find the lowest number for them to be on. So kind of makes sense for us to count going this way as opposed to this way because there's a lot more carbons on this side. So let's do 1, 2, 3, 4, 5, 6, and 7. So now we have a methyl on 2, and because this carbon 2 has this methyl group, and this carbon 3 has this methyl group. So we have a methyl on 2 and on 3. So the way that this works is you're not going to do 2-methyl, 3-methyl heptane. The way that they like to do it is 2,3 dash dimethyl heptane. So this is the parent. This is the substituent. Well, the substituents. The di is telling you that there's 2, and then these are their locations. Okay? You're eating it up. This is easy. You're gonna get it. It's gonna be okay. It's gonna be fine. It does get more complicated, but not harder. I'm falling off my chair. Now let's talk about what happens when you start adding functional groups. I'll add an alcohol group. So a hydroxyl group looks like this. So it's something bonded to an OH, right? This is known as a hydroxyl group. And it's in alcohols. This is like what characterizes alcohols, right? So you can have something like this. What is this called? Tell me what this shit's called. This is butane because it has 4 carbons. Mary eats peanut butter. Mary eats peanut butter. I'm losing my mind. Anyway, 1, 2, 3, 4, this is butane. Now what happens if I add this? 1, 2, 3, 4. 1, 2, 3, 4. Lowest carbon is 2. 2-methylbutane. That's how fast you guys will be able to do this, if not already. All right, whatever. Who cares about 2-methylbutane? Let's do OH. Like I said, I have ADD. Let's pay attention. All right, now let's say I have an OH right here. Same thing. What's the longest chain? 1, 2, 3, 4, 5. Pentane. I also do this on exams and everything. I just write it on the side and later I can refer to it because I don't want to say pentane, come back and I wrote heptane or something that's really similar sounding but wrong. So I just make sure to write everything and double check. Now, what is our substituent? We have this functional group, this hydroxyl group, right? So what are we going to do about that? We are going to name it. Same thing. Give it the lowest number. 1, 2, 3, 4, 5. I'm not going to count this way because there's hella carbons in the way and that's going to have a super high number that we don't want. We want it to come first in line. OH is very important. It's on the branch. She's separate. She's different. We love her. So now it's going to be 2 with the OH, right? This is just kind of me writing down what's present and what I need to number in the number that it has, if any. So this is going to be called 2-pentanol. 2-pentanol. Why is it not pentane, 2-pentane? Because now it has a functional group that is more important than the straight chain alkane. The OH group is super complex and it's adding a lot of like dimension and character to this compound. And essentially it wants to be pristine and super important and well known. So I just remember that if you have any important functional groups like CHO, which is an aldehyde, COOH, which is a carboxylic acid, COOCH3, which is an ester, any of that, it's gonna change the name, usually, of the parent chain ending, right? So now we know this is pentanol. How can you remember that it ends in OL? Because it's in alcohols. This is an alcohol, also known as a hydroxyl group. So it's a pentanol. This whole thing is an alcohol, pentanol. A lot of the times when they're on the first carbon, they don't number it because it's assumed that it's on carbon 1. But technically it would be 1-ethanol. You can also write it as ethan-1-ol because that tells you that the OH is on the first carbon. You can also do it here, pentan-2-ol. But it depends on your professor. It depends if it's multiple choice, if it's written, if they accept both forms, but both forms should be accepted because they are right. On that same note, we know that these important functional groups change the parent name. Same thing. If you were to have something that looks like this is a different functional group. This is a carboxylic acid, which looks like this. So it's C double bond O, OH, Q. Carboxylic acids are Q. I don't use that. I don't know why the fuck I said that. Anyway, back to what I was saying about the carboxylic acid. This is a carboxylic acid functional group. It's going to change the ending of the parent chain, just like last time we saw with the alcohol. Now, same thing. Longest carbon, 1, 2, 3, 4. There's 4 carbons. Butane is the beginning. It's not going to be butanol because it's not an alcohol. It's a carboxylic acid. So this would be known as butanoic acid. And I'm not going to put a number because it's on the first carbon because it's the lowest priority. But I'll put it, I guess, just for fun. Do you know what functional group this is? Down here, even though I drew it kind of dumb. This is a ketone right here. So if you have a long chain like this, obviously same thing. Parent chain, 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be octane. Would be the longest parent chain, but then you have a ketone. So the ending would be -one. So I guess an easier way to remember is that an aldehyde ends in -al, a ketone ends in -one, a carboxylic acid ends in oic acid. What else? An alcohol ends in -ol. This bitch is called octanone, but not just octanone because you need to lower the priority. So 1, 2, 3, 4, 5, 6, 7, 8. I'm numbering it all for cohesiveness, not necessarily because I need to number all of those, but remember we want to give this, the priority group, the smallest number. So it would be on 3. So it'd be 3 octanone. Solve this. I'll give you guys like a minute to pause. Okay, so longest chain, lowest, we're gonna assume priorities now. So obviously the bigger groups, usually like the more important functional groups, will try to get the smallest. We want everything to have the smallest number possible. So let's see how we can number this to give everything a smaller number. 1, 2, 3, 4, 5, 6, 7. So let's see if that's an option, or 1, 2, 3, 4, 5, 6, and 7. So in the pink numbering, where I counted this way, we have a group on 2, a group on 3. You see a group on 2, a group on 3, and then we have the carbonyl on 5. Okay. Now the groups that I counted this way, there's going to be something on 3, 5, and on 6, right? So obviously we're going to go with the way that we counted in the pink just because it has lower numbers. All right, now let's name this bitch. So longest chain, heptane, which is 7. Well, the longest chain is heptane, but because of this ketone right here, it's going to be heptanone. Or hepta-5-one. All right, let me show you how to do a double bond or an alkene real quick, just because I think it's simple, especially if you've made it this far. All right, what is this? Normal, 1, 2, 3, 4, 5. Pent something, pentene, because it's an alkene, because it has this double bond right here. Now, what's the lowest number we can give to the double bond? 1, 2, and 3. So either it's between 2 and 3, carbons 2 and 3, or it's between 1, 2, 3, and 4, right? So if we count it this way, if we were to count the carbons going this way, 1, 2, 3, it would give the double bond a smaller number and it would give it more priority, which is what we want. So we're gonna put 2 pentene. Or pent 2. Let me know if you guys have any other questions or if there are any more orgo topics that you would want me to cover. I did not do chirality in this video because this one was going on for a bit longer than I wanted it to, but I do expect to make a chirality and chiral centers and stereoisomer video soon. Bye!